Hi, everyone. Good afternoon. First, I want to make a quick announcement regarding the grade estimate that I posted on Blackboard. You should see a few different columns. There will be a pre-lecture column with all the pre-lectures counted till last week. Also, the homework averages for the, I believe, first 11 sets of homeworks. Or was it 8? I have an announcement on Blackboard as well. And also you have your two exam, each counts for 20% on that grade estimate. There's also an extra credit of the pre-assessment that you did at the beginning of the semester. If you did those, that's a 1 point out of 100, so 1% added to the grade accumulated grades. So how do you interpret the accumulated grades? All of its components, so those are 65. Those are 70%. So the accumulated grades that you got is out of those 70 points. We still haven't done the final. Final is 30%. So you can assume a score you get on the final, right? So assume you got 80 on the final, 80%. So 80 out of 100 points. So 80 times 30% of that will be added onto the accumulated grades you got, right? So if you accumulated let's say 55 points so far, and if you got 80 on the final and 30% of that is 24, so you add 24 with 55 and 79 will be your final grade. So that's how you interpret that. I did give you a estimate of the points on the final you will need, and out of 100, of course, if you have, if you want to get a 65 C minus, which is currently what is the passing grade in the syllabus. So this is how much you would need on the final. So just to give you an idea, but as you know that if you continue to do the homework pre-lecture, all of those scores will be updated slightly. They'll be slightly different. There's a post-assessment with a 1 point extra credit. So those will all be updated accordingly at the end of the grade calculation. Okay. Also, I do most of my curving at the end. So if I do end up doing curving, you know, it will be in the direction of helping students. So it will not be more harsh than the grading scale that is already in the syllabus. Okay, so just to give you an estimate of what is that you can expect. Okay, if you notice anything wrong with your grade that's been posted in the Blackboard, then feel free to let me know. If you feel like, okay, I think I have done way more homework, or I have done way more proof like that's not reflected in here, you should let me know, okay? Any questions?
So the total points for the class is 70, right?
The total points at so far, because all the components, the pre-lecture, homework, those add up are that's 70% or 70.
Oh, okay.
So the accumulated is out of those 70, how much you have gained.
Okay. Thank you.
Any other questions? Accumulated out of 70 is your current standing in the class, yes. But I think the better way to do an estimate for yourself is to set up a target for yourself. Let's say if you want to get a B minus in the class, that's how much points. And you need to see, I have already accumulated this much points. How much more do I need on the final to get me there? So that would be a better, more of an accurate estimate for your group. And you can also set up a goal for yourself. There's also a question, what is a final cumulative, or is it just gonna be on the last unit? In the past, it's always been cumulative, but there will be a slight strong emphasis on the later topics. So ever since stuff after the conservation of momentum, so we started rotation, right? So rotational kinematics, dynamics, conservation of momentum, and static equilibrium is the one we are still discussing today. And after that, you have universal gravitation, simple harmonic oscillation, and the fluids. There are only so much questions, right? So you can kind of guess how much questions you will get from each topic, because each topic will need to be covered a little bit in the exam. So the exam is cumulative, but it will be more focused on the later topics. What is the total amount of points for the class? Well, everything will be calculated out of 100, right? Is that what you mean? When all the assignments tests are finally in. Oh, well, everything is just calculated out of percentages. So no matter how many assignments you have, I still calculate percentages. So for example, if you get 95% of all the homework, no matter how much homework, I calculate the average. So, you know, and in 95% will be not, I will treat it as 95 points out of 100. How many questions does the final have? I can give you, I will soon upload a practice exam, but again, we have always done our exam in the classroom setting. We haven't done it in online. So for the exam, a final is usually longer than the actual class. The actual class is 75 minutes. Our final was 2 hours. So maybe 1.5 long. Questions will be proportionally longer. So if we had, was it 20 questions on the midterm, we probably will have somewhere around 30 questions on the final. And the time will be much longer too. It will be 3 hours instead of 2 hours. So it will be somewhere around 30, give or take a couple questions. Is there any way you can open up the homework for day to do any missing assignments that we have missed earlier on? I could do that in the flipped physics, but I don't know. Are you requesting it for everyone? I could open it up, the homework, just to let it do at the end of the last week. So you can still use that opportunity to study for earlier topics if you wish. Yeah, I could do that. Yeah, final will be like the midterm multiple choice questions or free response, in the sense you have to enter a numerical answer. Yes. All right. There will be a calculation. Yes, there will be some calculation in the final. Some conceptual questions, some calculation. Some calculation will be in the format of just choose the right answer, A, B, C, D, or E, or some of the calculation are like enter your number. So if you enter your number, because everybody might be giving a different value, so there will be some type of those questions. Those would not be the majority. The majority will just be choosing from A, B, C, D, E, just like the midterm. Okay, any other questions? Thank you all for asking these questions. I'm sure others are wondering about as well. So thank you all for asking. Okay, if you think of any questions, feel free to let me know, okay? And also take a look at your grade estimate. If you notice that there is a mistake, let me know as soon as possible. Okay, today we'll go back and finish our discussion on static equilibrium. And then we will touch a little bit on universal gravitation. Okay, so first let's finish this discussion for static equilibrium. So we've been talking about, if you want an object, a rigid body, what is a rigid body? It's not a point, right? It's an object. It's a continuous distribution of mass. So the rigid body needs to be stable. It needs to be in static equilibrium, means not moving, not rotating, which means all the forces has to be zero, add up to be zero, and all the torque has to add up to be zero, right? That's what we mean by static equilibrium. So let's take a look at the question. You have a door being pushed by 2 forces. One smaller is at the doorknob, is like to the edge. The larger force here is closer to the hinge. The door does not move, so the door is at static equilibrium. So can you conclude Well, just these two forces, the big and small, obviously they're not balancing each other out. For all the force and torque to balance, what is the force exerted on a hinge? In what direction? So I'm not gonna let you go ahead and discuss this. After you come back, you could go ahead and vote, okay? All right, 10 more seconds. If you haven't voted already, please put in your vote. All right, any last minute vote? If not, I'm going to end this. Let's take a look. All right, so it looks like the majority of the answers are either A or means 0. There's no force on the hinge, from the hinge, or points down to the right. That's D. So let's see which one it has to be. So we're saying that for the door to be at equilibrium, does not move, right? You need all the forces to cancel, to balance out. So now you have one big force, one small force. Without any force from the hinge, do you think the door will be balanced? One quick way to look at this is to look at forces in the X and Y direction. So your small force, you can break it into an X component to the left, right, and a Y component downward. So now it looks like you have a force to the left, have a force down, and you don't have any force to balance the horizontal force, right? So in order for the force to be balanced in the X direction, you need a force pointing to which direction? So this one is to the left. I need a force from the hinge pointing to which direction in order to balance that?
To the right.
The right, very good. Also, do I need a force in the perpendicular direction? Right now I have one downward. I also have one upward. Are these two balanced out? Do I need more?
There needs to be a force in the downward direction.
Ah, yes. And why is that?
Because the magnitude of the big force is greater than the smaller force.
Ah, this is smaller, right? So the component is even smaller. It's not going to be enough to balance this big force. So you need another small force to balance. You can see there should be these two forces from the hinge, and they add up to be in the sort of lower bottom right direction. So pointing diagonally downward. So another way also to look at this, okay, just by force alone, we realize the direction of the, we can figure out the direction of the hinge. Is the torque also balanced? You don't need that to answer this question, but we can certainly look at it. So when we say a torque is balanced, meaning that all the torque that attempt to rotate the object add up to be 0. So when there is a rotation, you need to define relative to which axis. So here is the door. So it makes sense to put our axis right here at the hinge. So all the rotation is relative to that point. Okay, it's not the only option. You can pick it wherever you want, but we usually pick it so that one of the forces goes away. So for example, here we're saying all the rotation is relative to here. So there are 3 forces, right? The big force 1, small force 2, the hinge force 3. If you pick your axis of rotation right here, you can see you do not have to evaluate the torque from the hinge. And why is that? I claim the torque by the hinge is 0. Why is that?
Because the hinge is the axis of rotation.
Yes, the hinge is the axis of rotation, which will make this radius level arm R0 for the torque. Right, the force is already at this point, right? So the distance from the axis of rotation to where the force is applied, well, the force is at the same location. So R is 0, which make the total torque is 0. So make it a little bit easier. We only need to look at the torque from these two. And you can see that the horizontal force, what is horizontal force doing? Is pushing in. It's not really gonna cause a rotation. The only force that's causing a rotation is the downward force from the small force. And also this downward force is attempt to make it rotate clockwise. The big force, upward force, attempt to make it rotate counterclockwise. So does it look like those two can cancel? Someone might argue, well, they cannot cancel because one force is bigger than the other. So the torque cannot cancel. What do you guys think?
I think the torque could cancel if the applied force was in the right place relative to the axis.
Where you apply it also matters. Very good. So torque is R cross F. So even though the big force is bigger, is applied at a smaller distance, you have a smaller level arm. So it can cancel out the smaller force, even though it's smaller, but it's applied at a much longer level arm, so that these two still cancels, right? Give you overall torque is 0. So indeed, the door is at static equilibrium. Let's look at another question. So here we want to figure out not only which the directional forces, but also the magnitude, the ratio of the forces. How do they compare one to another? Okay, so we are giving the force diagram already. This is a very light board supported at the ends. So you don't have to think about the weight of the board, but there is a mass on top of the board, that's M. So there's a weight applying, that's mg on the board, right? And from the two supporting points, you have normal force. We call it the force from the left and force on the right, at the right. So how do these two forces compare to each other? So there's a hint. Consider the torque around the mass M. So it's at static equilibrium, so the torque, sum of the torque has to add up to be 0. Okay, I'll let you guys discuss this and then we can talk about it. Okay, so let's go for 10 more seconds. Okay, any last minute vote? All right, let's take a look. This is our voting results. It looks like we are pretty much all over the place from A, B, C, D on quite evenly distributed. Okay, so what is at play here? We wanted to compare the ratio of those two forces. Which one is bigger, right? F right over F left. What is the ratio? We know it is this, this whole thing is at static equilibrium. The forces or all the torque that's acting on the board should be balanced out. Here it's asking us to consider the torque around mass M. Okay, so which means we are investigating rotation around this point. Okay, so all the torque has to add up to be 0. So there are only 3 forces, so we can only get a torque from 3 different sources, right? The gravity of the M will generate a torque. The force from the left will generate a torque. The force from the right will generate a torque. But here you can see we deliberately choose the rotation to be at the point where the mg is, because we want to compare these two forces, right? So if we choose our axis of rotation to be right here, we can get rid of the torque from the mg. It's just a little bit more convenient in terms of our calculation, okay? So we don't have to worry about the torque from the mg if we choose to look at rotation from that point, relative to that point. So really it's just the torque from the force on the left has to balance out the torque from the force to the right, right? One of them is attempting to make it rotate this way. The other one is attempting to make it rotate the other way, and they have to balance out. Okay, so now looking at this, can you guys tell me which force do you think is bigger? Left or the right?
The right force?
The right is bigger. And why is that?
Because it's closer to the
The
axis of
force to the right.
rotation.
Yeah.
Yes, thank you. Yes, there is a smaller level arm, but generate a same amount of torque, right? F on the left, you can see that this is how the level arm compare. This one is 2/3 of L, this is 1/3 of L. So the R left times force left is equal to R right times force right. But R left is 2 times the R right, twice as long, right? This is twice as long as the other one. So you have twice the level arm, but produce the same amount of torque. Of course, the F left will be smaller. Right? So F left will be 1/2 of F of R, or in other words, the force on the right is twice as much of the force on the left. Right? So if you first look at this qualitatively, in the sense of this one has a longer level arm, this one has a shorter one, which means this force is bigger. And you can go through all of these. You can get rid of the ones that give you a ratio that's smaller than 1. You know that these are all wrong, and it has to be 2, right? Or if you don't know, then you can do the calculation to see if it's indeed 2 or some other ratio. Okay, so you can see this is a direct application of the torque equation. Whether we wanted to look at the force equation first or the torque equation first, depending on what question is asking. But you know that eventually if you combine both of these questions, you can solve for all the quantities that you need to know. And also where to set your rotational axis depend on, again, what question is asking. Okay, so this is the correct answer is D, 2 times as much. This is a homework question. Okay, so let's do this one together. We have a purple beam is hanging onto, is being pulled up by a tension, a cable right here. And on the one side of it, there's a sign hanging onto it. And the beam has a particular type of mass. The sign has another type of mass. The length of the beam is given, and there's a rope and there's some tension in the rope. So it's asking, the first question is, what is the tension in the wire? Okay, so what is the tension in the wire? I want you to go ahead and draw the free body diagram on this picture, or if you have your notes right next to you, you can duplicate the picture and draw a free body diagram that's on the beam. Okay. Once we have the free body diagram, we'll set either force equal to 0 or the torque equals to 0 to calculate the question is asking. So right now it's asking for the tension. So the first step is to draw the free body diagram. So I'll give you a little bit time to draw it, and after you draw it, then let's talk about it together. Okay, have you drawn the free body diagram yet? We can go through the forces one by one. I will not ask you how many forces you draw, but instead just if you have drawn one force, tell me what it is. So can you guys give me a force, just any force that's acting on the beam?
The tension force and the force of gravity on the object.
Yeah, tension from the cable. And with this tension, would it make sense that it's to the right? Okay, and the gravity, and would you want to draw the gravity due to the sign or the gravity due to the mass of the beam itself? Or both? Both of them. Okay, so let me draw the mass. So on this one end, you will draw a force M sine G. And I also need to draw the gravity of the beam. So where should I put that gravity? Should I put it here, here, here? Where would I put it?
Center of mass.
Center of the mass of the beam, and that's in the middle of the beam because it's uniform. And the mass is otherwise, if it's specially noted, it's always uniform distributed, so it's right in the center. Okay, so that's also tell you if you need to calculate the level arm of that force, implicitly already told you where it is, right? It's right at the center of the beam, and there's a gravity M of the beam, G. Okay, so have I drawn all my forces? Do you think there could be other forces acting on the beam? Just by looking at it, do you think they can, right now, they can reach some kind of equilibrium?
There's a normal force coming from the wall.
Okay. And in what direction? To the left, to the right, up or down?
The opposite of tension.
Okay, very good. You know there has to be a force here, right, at the hinge, if you call this the hinge, because you can see right now you have 3 forces, 2 in the vertical direction, 1 horizontal. There's no way for these 2 to balance out each other, right? So you need another horizontal to balance out the force to the right, the tension, under the hinge force to the X direction. And is there anything else? Right now, do you think it's at static equilibrium? This direction seems like it can be balanced. What about this direction?
There's more normal force from the hinge going up as well.
Yes, there's another force from the hinge to balance out the weight. So I think at this point, you can say, yes, we have drawn all the forces we have, and we're ready to do our calculation. First question, what is the tension in the wire? Okay, so you can see we don't really know what the tension is. We know what these 2 forces are. We don't know what the force from the hinge is. All of these are unknown quantities. So if you, obviously, if you set up all these equations, you can solve for all the unknowns all at once, right? How many unknown quantities, how many equations? But sometimes we prioritize which equation we want to use first, depending on the question. Here, it's asking what is the tension in the wire. So if I'm able to eliminate some of the forces in my equation and leaving only the tension and some known quantities, I can solve for the tension in the wire first, and then I can worry about the other forces, right? So, so I want to eliminate the force from the hinge because I don't know what it is. I don't want to think about it right now. So what do you think is a good thing to do? Should I go ahead and set up my force equation or torque equation first? Should I do this one first or this one first?
Do the force.
If I do the force one, I can say the tension should balance out the hinge force in the x direction. I don't know what the hinge force is, so I'm stuck. You can say the hinge force in the y direction balance out the gravity. Okay, so I can solve for my y, but that doesn't tell me anything about the x. So I still don't know what tension is. Then I also have the torque equation. I tried the force, it didn't help me, and I can go to the torque equation. So I'm going to the torque equation. Where do you think I should put my axis of rotation? Where do you want to put your axis?
At the hinge.
Right at the hinge. Very good. This way I can eliminate the torque from the hinge. So I don't have to worry about it. Okay, now let's set up the torque equation. So I tell you, what do we do? We will think about the torque equation like how we set up our force equation. There's a positive torque and a negative torque. And for those who generate positive torque, you put a plus sign in front of it and you add the magnitude. For the negative torque, you put a minus sign in front of it and then the magnitude. And then when you do the magnitude, you don't have to worry about the minus signs or directions anymore. It's already taken care of. So I'm going to set up my X and Y. This direction, X, Y. So X and the Z direction is pointing out of the page. So a dot sign represents out of the page Z. Okay. So and then we can look at the torque generated by these forces. The gravity, you can see that they are trying to attempt to rotate this entire beam in this direction, and the torque is trying to rotate them in the opposite direction. Whichever you set to be positive or negative doesn't matter as long as you're consistent. So our convention says I will choose my clockwise, counterclockwise to be positive and clockwise to be negative. So here would be the torque from mg plus the torque from another mg minus the torque from the tension. Well, here are only the magnitude. Okay, I've already taken care of it. And then the next step is you're going to use R times F to calculate each one of them. And you want to use the perpendicular component of R, okay? So this is the first radius, this is the second radius, this is the third radius. They're all at a different radius. Okay, so it would be better if we start drawing the level arm, the perpendicular distance first. So let's look at the first one. This is mg, and you can see the perpendicular distance from the center of rotation to where the force is, right? Perpendicular is this distance right here. And that is L times cosine theta. Okay, this is theta.
Oh, it's
L is the length of the beam. And if I draw a little dash line right here, it's horizontal to my cable. Sorry. That is theta. This is theta. Okay. So this is L, and this side is L times cosine theta. That's why. And let's figure out the other level arm. And this is my other force. Again, I want the level arm. So from the axis rotation to where your force is, you have a perpendicular distance. And this distance you can see is L over 2 times cosine theta, because the hypotenuse of this is L over 2. Okay, so that distance is L over 2 times cosine theta. Okay, so these might take a little bit time to work it out in the diagram, but once you work it out, the rest will be easy. You simply are plugging into your torque equation. The third one is the level arm for your tension. Okay. This is your axis rotation, and this is your tension. The perpendicular distance is from here to here. This is the vertical distance. Okay. And what is that? You can see that inside this triangle, I'm going to highlight it. In this triangle, this is theta. We want to know this side, and the hypotenuse is 2/3 of L, because it tells me that the tension is applied 1/3 of the way, or 2/3 of the way to the end. So from here to here is 2/3 of L, and sine theta gives me this side. You label your level arm first, and then you can plug in into your torque equation. Okay, the torque from the sine and the beam, those are all positive torques, because it's making the thing to rotate counterclockwise. So that's why it's positive sine and positive sine here. The torque from the wire is negative. And then you plug in the radius times the force. The force from the sine is mg. The distance from the sine is L sine theta. The force from another beam is different mg, and times a different radius. And the tension times a different distance. Okay, so we want to solve for the tension, and this equation gives you tension simply just from the torque equation. This is your final results for the tension. Okay. So I'm gonna pause for a few seconds. Looking at the diagram and my equation, are there any questions? Are there any questions? Okay, I know setting up these torque equation static equilibrium might be complicated. So here is an opportunity that we can ask questions.
Did you factor out the L and then got rid of it by dividing it to the other side?
Yeah, I canceled L because they all have an L, which I can cancel them. This side is 0, so I can cancel my L, right?
Oh, okay.
Yeah. Or you can view this as you put this to the other side and then you divide both sides by L. So it's the same thing as canceling it. Oops, sorry, what happened? Yeah, thank you for asking that question. Any other questions? I think the difficult part is figuring out what each of the torque is. That is the difficult part. So you need to look at the force and then this L perpendicular. Okay. Torque is R cross F. Okay. So let's say if this is your force, and this is your R, and you can see they have an angle, right? doing the cross product is equivalent of looking, okay, this L, which part of this L is perpendicular to F, is equivalent of using this perpendicular component times F, R perpendicular times multiplied by F, because the cross product needs a sine theta, and sine theta is really just giving you this perpendicular component. That's the level arm that matters. You have a horizontal component, but that doesn't contribute anything to your cross product. Okay. All right. So now let's look at the next question. Okay. The next question is, what is the net force in the hinge? So you figure out the tension. You want to figure out what is the net force in the hinge. The hinge has two components. It has the X component and the Y component. Well, you know, these two are easy to calculate now once you figure out tension, because the Y component has to balance out the two gravities. The X component has to balance out the tension. You know each of them, right? So now I know, now it's the time to use my force equation. I've done the torque equation first, then I do the force equation. The X component has to balance out tension, so whatever tension you calculated, it's equal to the magnitude of your hinge force, X. And the two gravity combined is going to balance out the hinge force and the Y. And if you are asking about the net, which is X and Y combined, then the total is X squared plus Y squared, square root of that, right? Because if you have a X and a Y, and this net force is going to be the root of X squared plus Y squared, because this is a triangle and it's 90 degrees between X and Y. And the hypotenuse is going to be like that. Okay, so you can calculate the net force once you plug in the equations. The third question is, what is the maximum tension the wire can hold without breaking? And it tells you the maximum tension the wire can have is this much limit. And what is the maximum amount of mass of the sign that you can harm from the beam? So you can see by deriving this relationship in the beginning and keep this format without plugging the equations, now you can plug in whatever equation you want, numbers you want. Here, if I set my torque to be the maximum amount of tension I can handle, then you can see on the right-hand side, I can calculate the maximum amount of the mass that this wire can handle. Right? You can solve for n by plugging tension equals 891.
Professor, for the last the last problem where we're trying to find the hinge force,
Yeah.
could we change the hx to just h cosine theta equals tension?
Hx is h cosine theta and equals tension. So
Yeah.
yeah, you could do that. Let me see if the theta is the same. Yes, so okay, I'm gonna highlight the angle here. So this is theta. Okay, this is horizontal. This is horizontal. Right? This is theta, which means this is theta. So if this is theta, yes, the adjacent line would be hx, which is h times cosine theta, and that equals tension. That is okay. So
Okay.
I understand what you're trying to say. So you're saying instead of calculating them separately, you can say because the hinge force times cosine theta equals tension, and I know this theta, I can calculate this tension right away without doing the y component, right?
Yes.
Yes, you can totally do that. A very good point. You can also do that. Okay, so that is a demonstration of how we combined use torque equation and force equation to solve for a static equilibrium question. You can see whichever question, whichever you use depend on whatever it's asking. So here we use a torque equation first, because you can see from the torque equation, we can eliminate the hinge force that we didn't know and solve for the tension. Then use the force equation to solve for the hinge force later. And in terms of choosing the axis of rotation, we always put it in a convenient place so that we can eliminate the force and that we don't know, and we can calculate the rest of it that's relevant. Okay, so that's what we're going to discuss for static equilibrium. For the little bit of time we have now, I'm going to shift gears. We're going to move to universal gravitation. Before I move on, any questions so far about this particular problem? All right, let's go look at universal gravitation. I'm going to start out with a question, simply just sort of brainstorming question. I'm going to throw it out here. There's a famous Leaning Tower of Pisa. Historically, the story goes that Galileo was doing a famous experiment, right? He was wondering about different objects with different masses. Would they fall at the same rate? Is a heavier object go faster? Like Aristotle thinks. Back in the olden days, Aristotle's age, people think the heavy object falls faster. So Galileo took an interest in that and performed this experiment on the Leaning Tower of Pisa. Of course, we don't really know today if he really did the experiment, but the story goes that he did this experiment and found, surprisingly, it's not like that. They almost fall at the same rate, similar rate. And that is the very first controlled experiment we ever did in physics. So my question now is something else. Why this Leaning Tower of Pisa does not fall? So does not fall means that it is at static equilibrium. So I want to use this to sort of put a capture on our discussion. Do you think these two equations are satisfied for this Leaning Tower of Pisa?
Yes.
Okay, so which two, how are they satisfied? All the forces acting on the tower. What kind of forces acting on the tower?
Gravity and normal force.
Yes, gravity. Normal force is coming from the base, and where would the gravity be acting? At the center of the mass, right?
Right.
Yeah, so let's say approximately somewhere here, you should have gravity, F of G, or weight. And from the base, you should have normal force. So gravity is down and normal force from the base is up. It makes sense that, yes, force-wise, it seems it can be balanced out. And torque-wise, is it balanced?
No, there's also a frictional force.
Yes, there might be also friction at the base, but it's really hard to talk about it when something is a solid object connected to the base. It's not something that's just been set. It's, you dig in, you have these concrete, so it's really hard to say it's a frictional force. So we're only just going to consider the effectiveness, the effect of the gravity and the normal force, because it's just one down and one up. So I would argue that the torque is also balanced in the sense that we need to look very carefully at the center of the mass. So if an object is standing on its base and it will not fall, will keep standing, until this gravity, the force of the gravity going away from the base, then it's going to tip over. Because as long as this force is still within the base, you can see the normal force are still going to, so this gravity, we're trying to make it fall this way, but you still have a normal force not trying to balance out the torque that way, you can still stand. But once you can see if the gravity shift away from the base, you are not going to be able to prevent it from falling. That's why sometimes when you have an object, you tilt it a little bit, it's still standing, but once you add more and more mass onto the top, you're shifting your center of the mass higher, shifting a little bit higher. And when we say our center of mass is higher, we're less stable. And why is that? That's meaning that you're moving further away from your base, right? If you add something on the top, you're moving even further away from your base. Again, you can see that you can inevitably you have to fall. The torque is no longer balanced. So I just want to use this as a quick recap of what we had just discussed. Another famous scientist, Galileo, right? You probably heard of Galileo. Another famous scientist that you heard of probably even more is Isaac Newton. And here we're talking about his great discovery of gravitational force, the gravitational attraction between stars, planets, or any objects that has mass. So he made this discovery 45 years after Kepler, who's another astronomer who made observation of the orbit of the planet and carefully graphed how the Earth orbits around, and then, as well as some of the other planets in the solar system. So again, there's always goes with the story, but I really nobody knows. It's what Isaac Newton said below an apple tree, and the apple that hit his head inspired him to think about the gravity that makes the apple fall. Is the same amount of is the same mechanism as the gravity between the Earth and the Sun. Same mechanism that is responsible for keeping all the stars in its orbit. But it's another story. So the universal gravitation states that as long as you have two objects that has mass, then there is a gravitational attraction between them, right? So any object with mass, so your computer and you, there's an attraction. You and the Earth, there's an attraction. Between your backpack and your computer, there's an attraction, even though it may be small, but it's there. So here are some questions that that inspired Newton to come up with the discovery of the universal gravitation. Start with thinking about the planets that are moving around the sun. What force is keeping them in orbit? Right? We know that we need centripetal force for a circular motion. And what kind of force is serving the role as the centripetal force? What force is keeping the moon in its orbit, similar to what is keeping the other planets in its orbit? Could the force of gravity be universal? And yes, it is, as later on Newton discovered. So you can see that why the moon is not going to fall into the Earth, right? You may ask that question. If there's attraction between them. This is just like how we asked earlier, right? In our previous chapters, is why won't you fall off the roller coaster, right? That is because you have a velocity this way. You're doing a circular motion, and the force is serving as the role of the centripetal force. It's giving you a centripetal acceleration. You simply are changing your direction of your velocity, right? Instead of falling down, you're simply changing the direction of the velocity. You're following a circular path. So Newton's law of gravitation states, any two objects attract each other with the gravitational force, and the amount of this force is proportional to the product of their masses. So the more massive it is, the bigger force you have, and inversely proportional to the square of the distance between them. So you will later on in physics see a lot of the forces that obey this inverse square rule. That is, as your distance increase, your force decrease as a function of 1 over distance squared. The force acts in the direction of the line connecting the center of the masses. Right, so for example, you have two masses, M1 and M2. Their distance between the center of the masses is R. So the attraction between them is G, the gravitational constant. The product of the masses, mass 1 times mass 2 divided by the distance squared. So this is really, this equation describes what Newton's law of universal gravitation was talking about. So when you're on Earth, so you can use this general equation to calculate the force between you and the Earth, right? So it will be constant, the mass of you, the mass of the Earth, and the radius between you and Earth. If you're standing on the surface of the Earth, then the distance between you and the Earth is roughly the radius of the Earth, right? So this force is approximately mg, little g. Okay, so we simplify this a little bit when we did Newton's law, when we do gravity. You're simply using your mass times this little g on Earth's surface, because whatever object you're talking about, whether it's you or your book or a rock or a mountain, they all share the same constants, right? They share the g, they share the mass of the Earth and r squared. So we're just going to use the little g to represent that constant, right? That's where this little mg comes from in the beginning. But you know that it's more universal to use this equation, okay? So this is an attraction, right? No matter what it is, the force is always attracting each other. So you can use this to explain why the moon does not fall straight onto the Earth, because this universal gravitation, F G is G, mass of the moon times mass of the Earth times the distance between them, is now serving, giving the centrifugal acceleration of the moon. So G, as we said, normally in daily lives, you never notice the gravitational attraction from any other objects except Earth, right? You only feel like we have our weight. That is the only force that is noticeable. The attraction from any other object, the big building, the mountains, have very little effect on you. And why is that? Is because this G is very, very small. It's a very small constant. So how do people decide this constant? How do they even measure it in history? So the famous Cavendish experiment determined the gravitational constant, and I think it's very neat. The design behind such experiments can be used in many other different measurements. So how did this scientist decide this constant? Well, there is an attraction between objects, right? So he created this torsion balance with a string attached to the beam. On two sides of the beam, you have a little mass, a little ball on each side. And you put a bigger mass, this one is behind the first ball, and this one is in front of the first ball. So if they're attracting, right, this one will try to give it attract it this way, this one will attract it this way. And you can see as a result of that, this one is being attracted backwards, this one is being pulling forward. So as a result of that, this all of this torsion balance will rotate, because you have created a torque, right? You have created torque. So if it rotates, and there is a thread hanging the torsion balance, and also this little, but you say, now what, that rotation is so small, it's not visible to our eye. So how do you even measure it? There's a little mirror here. When you have a laser shining onto the mirror, and you can receive the reflection of the laser. And if you have a little tweak to the torsion balance, even if it's a little, the reflection of the laser is going to be changed, and you can observe how much is being changed, and figure out how much of the attraction is caused here and here. You can figure out the gravitational constant G. So it's a very, very clever setup and experiment. So they measured that in 1798. The value is extremely small. It's 6.67 times 10 to the negative 11 newtons meters squared divided by kilograms squared. And so this is the universal gravitational constant. So gravitational force changes with distance and it drops as 1 over r squared as your, it's called a inverse square law, which means force is proportional to 1 over radius in distance squared. As your distance increases, your force quickly dissipates and decreases very quickly because it's decreasing as 1 over r squared, right? As you go further away from the Earth, the gravitational attraction is smaller and smaller until it goes away and you are free of the Earth's attraction. It has a very small and tiny effect on the everyday object. In fact, you can try to do an estimate of how big you think that force is. For example, what is the attraction on the girl with a 70 kilogram mass from her back? You can assume a mass of the backpack and assume a mass of the person and put in the gravitational constant in there and assume a distance between them. How close do you want them to be, right? You can assume 0.6 meters between them or some other distance or closer or bigger. And you can calculate this force. You can see that it's still very tiny, 10 to the negative 7 newtons. So that's why it has a very minor effect on us when we are looking at the everyday object. Now, even if you put in a mountain, still compared with the entire mass of the Earth, that force is negligible. But if you calculate the force from the Earth, it's much more obvious, right? You can plug in the mass of the Earth and the radius of the Earth. The force acting on the girl is 700 newtons, obviously much more noticeable than the other forces. So when we're on Earth, that's why we only consider the Earth's gravity. We don't consider the other attraction from the other objects. But this force becomes much more important when you're considering the astronomical objects. For example, the attraction between Earth and the Moon, and the attraction between the Earth and the Sun. Or when you shoot up a satellite, right, you need to think about the attraction between the satellite and the Earth. It's keeping the satellite in orbit. So these become much more noticeable when you are considering astronomical objects. So let's do one more check one question that you probably have already done. Which one of these free body diagrams best represent the gravitational pull in the Sun-Earth system? Okay, so obviously this big orange dot is the Sun. This little blue dot is the Earth. So which one of these is a correct free body diagram between them? Which one do you think? So A has, which one?
C, because it pulls much harder on the Earth than the Earth pulls on the Sun.
I would think it's B.
Okay. So what is, if I'm asking the gravitational pull, how would you calculate it? Would you use the equation I gave you? Would that be applicable here? So you would use mass. This is between two objects. You have Earth, you have Sun. The force is proportional to the product of those masses. Mass of the Sun times mass of the Earth divided by the distance between the Sun and mass squared. So someone says, yes, the mass of the Sun is way bigger than Earth. So does that mean the force on the Earth will be bigger?
No.
In between them, yes. So this is an attraction between the two objects. See, we didn't specify mass 1, mass 2, and which one is it acting on? Is acting on them with the same amount. So the force on the Earth by the Sun is the same magnitude of the force on the sun by the earth. And we have learned this in the beginning of the semester. What do we call this? This is Newton's
Third law of motion.
third law. Very good. What does third law tell us? Can you remind us?
Every object that experiences a force experiences another force that is equal and opposite.
Yes, equal and opposite. Your sun pulling the earth with some force. The sun and the earth is pulling on the sun with the exact same amount, but opposite direction. So these two forces are action reaction pairs, and they're always equal in magnitude, right? So B is correct. And when you do the calculation, both of the mass will matter. Okay, doesn't really matter. So you may say it has a bigger effect on the Earth. Yes, it will, because Earth is bigger and it will give Earth a bigger acceleration, but it will have a very little effect on the sun. Just like when you're on the Earth, each of us is pulling the Earth just as hard as the Earth is pulling us. Right? If our weight is, let's say, 120 pounds, which means we are pulling the Earth with exact 120 pounds, each one of us. But the Earth is so massive, this force is doing nothing in terms of changing the Earth's status of motion, but it is indeed pulling on the Earth. So the correct answer is B. Okay, so that's all we can do for today. We will do more discussion on universal gravitation on Thursday. And again, take a look at your grade estimate. If you notice anything, please let me know. And did I announce that a change in the office hour? That I had to change it on Wednesdays from 3 to 4 to 12:30, 45 to 1:45. So take a note of that if you need to ask me questions. All right, I'll see everyone on Thursday. And bye. Have a good
Thank you,
rest of the day.
Professor.
Thank you, Professor. Have a good day.
Thank you, Professor.
Thank you. Bye-bye.